Tonight, let's drift together into the quiet vastness of the universe. The world outside begins to fade, the hum of the city softens, the night air slows, and somewhere between waking and dreaming, curiosity still glows gently, like starlight resting on your skin. We'll wander through the gentle pull of gravity, the slow dance of time, and the endless ocean of the cosmos. Not to solve their mysteries, but to feel them, to let their stories cradle us as we fall asleep. Close your eyes if you wish. Imagine yourself floating, not up, not down, just suspended in the calm of space, where every thought moves like dust in moonlight. Here, science is not a lecture, it's a lullaby. Each idea, a soft ripple in the dark. Each question, a quiet heartbeat in the stars. So, breathe slowly. Let the rhythm of your breath match the rhythm of the universe. And if this journey brings you peace, let your heart remember to like, to subscribe, and to return each night to this quiet space among the stars. When you gaze up at the night sky and watch the moon drift slowly across its dark ocean, or see a quiet streak of light sweep through the silence, you are witnessing the endless waltz of the cosmos. Every falling leaf, every orbiting star, every breath drawn beneath this sky moves to the rhythm of invisible threads. For centuries, we tried to name those threads, to understand why things fall, why planets glide, why everything seems so mysteriously ordered. For a long time, we thought of gravity as a force, an unseen pull between things. The greater the mass, the stronger the pull, the farther apart, the weaker it became. It was a beautiful idea, carried gently into the world by Isaac Newton. His equations guided sailors and astronomers alike, explaining apples falling and moons circling with astonishing grace. For 200 years, this vision held firm until the universe whispered that something deeper was hidden beneath. At the dawn of the 20th century, another mind began to listen to that whisper. Albert Einstein, patient and curious, began to wonder if gravity was not a force at all, but a story written into the fabric of existence itself. In 1915, his thoughts bloomed into a theory, general relativity, a new way of seeing not only motion and mass, but space and time themselves. Einstein's revelation was gentle, yet revolutionary. Gravity, he said, is not a push or pull, but the bending of space and time by energy and matter. The universe was not a rigid stage, as Newton once believed. It was a living fabric, soft and curved, responding to everything within it. Where mass gathers, space folds. Where energy flows, time itself stretches or slows. In Newton's picture, time ticked steadily, the same for everyone, and space was smooth, endless, and indifferent. Forces acted instantly, binding the cosmos together without any visible bridge. It worked beautifully, almost perfectly, but not quite. Something subtle in Mercury's orbit refused to fit, a tiny imperfection that puzzled astronomers for decades. It was as if one planet, small and stubborn, carried a secret that Newton's laws could not quite explain. Einstein's theory would reveal that secret. He imagined that space and time were not separate, but one continuous fabric, space-time. And gravity was not transmitted through emptiness, but born from the way this fabric bends and flows. Matter tells space-time how to curve, and curved space-time tells matter how to move. To describe this bending, Einstein turned to Riemannian geometry, a mathematical art that paints curves instead of lines, and surfaces that twist into dimensions beyond sight. With the help of his friends Marcel Grossman and David Hilbert, he gave the universe a new language. the Einstein field equations. They look abstract, symbols flowing across paper, but hidden within them are the orbits of planets, the expansion of galaxies, and the slow breathing of the cosmos itself. Einstein's insight came from a simple human dream. He imagined a person inside a sealed elevator, falling freely through space. Inside, that person would feel no weight, unable to tell whether they were falling toward the Earth or floating in the stars. From that quiet image came a profound truth. The effects of gravity and acceleration are indistinguishable. It was called the equivalence principle, and it became the heart of general relativity. In this new vision, gravity was not a force pulling down, but a natural path through curved space. The sun doesn't pull the planets. It bends the fabric around it, and the planets simply follow the smoothest lines, called geodesics, through that curvature. Much like airplanes tracing great circles across the globe, the planets follow their own effortless paths, shaped not by a tug, but by the landscape of space-time itself. Even light, that swift and faithful traveler, feels the curvature. As it glides past a massive star or galaxy, its path bends a silent arc through warped space. From Earth, we see this as gravitational lensing. Distant starlight bending around invisible giants, forming delicate rings and shimmering arcs. Space-time becomes a cosmic mirror, distorting and magnifying the farthest corners of the universe. In 1919, this bending of light was finally seen. During a total solar eclipse, British astronomer Arthur Eddington watched the stars near the darkened sun shift from their usual positions, exactly as Einstein had predicted. When the data was confirmed, the world awoke to a new kind of wonder. The universe had spoken through light itself, and Einstein's quiet equations became a doorway to understanding. But relativity was not content to stop at light and orbits. It reached into time itself. Einstein's equations whispered that where gravity is stronger, time moves slower. Near mountains, planets, or black holes, the seconds stretch ever so slightly compared to those in gentler space. This isn't a metaphor, it's a measurable truth. Scientists have tested it with exquisite precision, using atomic clocks placed at different heights. The clocks perched higher, where Earth's pull is weaker, tick just a bit faster than those below. This subtle effect, gravitational time dilation, keeps our GPS satellites accurate. Without accounting for it, your phone would drift miles off course each day. Even your morning commute depends on Einstein's dream of curved time. And then there are black holes, places where curvature becomes infinite, where not even light can escape the depth of gravity's embrace. Once, they were only theoretical, dark rumors in the math. Now, we have seen their shadows. In 2019, the Event Horizon Telescope revealed the glowing ring of one such cosmic abyss, the edge of space-time itself made visible. General relativity doesn't just describe local gravity, it tells the story of the entire universe. When applied to everything, to galaxies and stars, and the invisible stretch between them, it predicts that space-time can expand or contract. This was the birth of modern cosmology, and from it came the realization that the universe is not static, but growing. It began with a flash, the Big Bang, when all of space-time blossomed from a single dense moment into everything we now see. Astronomer Edwin Hubble confirmed this in the 1,920 seconds. Galaxies were drifting apart. Space itself was expanding. Later, the faint afterglow of that beginning, the cosmic microwave background, gave even stronger proof. Ironically, Einstein once resisted this idea. Wanting the cosmos to stand still, he added a cosmological constant to his equations, a delicate balance against collapse. When expansion was discovered, he called it his greatest mistake. Yet now, that same constant returns in a new form, as dark energy, a mysterious presence pushing the universe outward, faster and faster. Still, for all its beauty, general relativity is not the final word. When we try to apply it to the smallest scales inside black holes or the birth of the cosmos, the smooth fabric of space-time seems to unravel. Quantum physics, with its jittering probabilities and discrete energies, refuses to fit neatly into Einstein's calm continuum. Somewhere, beyond both, a deeper truth must wait a bridge, uniting gravity and the quantum world. And yet, even unfinished, general relativity remains one of humanity's greatest symphonies. It explains the curves of light, the tides of time, the slow dance of galaxies. It transforms the universe from a cold machine into a living geometry, supple, breathing, connected. Every atom, every thought, every heartbeat leaves a tiny imprint upon that fabric. You are not floating in space, you are of it. Your weight, your warmth, your pulse, they bend space-time just as the stars do. The universe curves around you, softly, endlessly. Gravity is not something that holds you down, it's what holds you within. In the hush of night, when everything feels distant, remember this: the same equations that guide the stars also cradle you to sleep. The same space-time that carries galaxies carries your dreams. You are not outside the cosmos. You are a ripple in its vast, gentle sea, forever moving, forever connected, forever home. To speak of the universe without geometry is like humming a melody with no pitch at all. Geometry is more than a catalog of shapes and forms. It is the blueprint of physical law itself. In general relativity, the geometry of space-time is not a painted backdrop but a living presence, an active companion in the slow, unfolding tale of the cosmos. Where classical physics once kept space and time rigid, unyielding, and absolute, general relativity replaces that picture with something gentler and more fluid. Space and time merge into one quiet continuum, space-time, whose shape and curvature are not fixed, but responsive, sculpted constantly by the matter and energy that move within it. The idea of space-time curvature is central to general relativity, yet it slips from everyday intuition. In daily life, space feels flat and faithful. Things travel straight unless nudged, and distances seem reliable wherever we go. But these are local truths, small windows onto a wider landscape. On cosmic scales, or near strong gravity, space and time bend first softly, then profoundly, like a vast sheet settling under invisible weight. To sense how this bending happens, we must think not only about motion or forces, but about geometry itself changing from place to place. Curved space-time is no figure of speech. It is a precise description of how distances between points and intervals between events shift under the influence of mass and energy. Much like a sheet of paper that can lie flat or fold into intricate contours, the fabric of space-time can be nearly flat or richly curved. Yet unlike paper, it does not bend into some higher arena we can step back and see. Its curvature is intrinsic, measurable from within, without any need for an outside frame to define it. Here, Riemannian geometry becomes essential. Born in the 19th century from Bernhard Riemann's insight, it provides the language to describe curved surfaces in any number of dimensions. In general relativity, space-time is a specific kind of curved, four-dimensional manifold, three directions of space joined with one direction of time. The curvature of this manifold is encoded in the metric tensor, a mathematical compass that tells us how to measure distances and times locally at each point in space-time. In Euclidean geometry, the metric is simple and still. In Einstein's world, the space-time metric is dynamic, shaped and reshaped by the distribution of mass and energy. If this sounds abstract, it is, and yet it rests firmly on what we can witness. The shape of space-time guides everything that passes through it. The sweep of planets, the flight of light, even the quiet pacing of time itself. Geodesic's paths of least resistance, the straightest possible routes through curved space-time, are written by the geometry the metric describes. In flat space, a geodesic is a straight line. On a sphere, it is a great circle. In space-time, it is the path a freely falling object naturally follows, even if to a distant onlooker, that path appears gently curved. What is profound in this view is that freely falling objects are not being pushed or pulled in the usual sense. They are simply yielding to the geometry already laid out beneath them. When Earth circles the Sun, it is not dragged in a Newtonian tug. It is tracing a geodesic through the curved space-time shaped by the Sun's mass. If, in a thought experiment, the Sun were erased while Earth's velocity stayed the same, Earth would no longer follow a bending course. It would slide away along a straight track in the now nearly flat geometry of empty space-time. Different arrangements of mass and energy etch different curvatures. A small planet makes a gentle hollow, a massive star, a deeper valley. A black hole marks a place where curvature grows so intense that geodesics spiral inward and no path finds a way out. These curvatures are neither imaginary nor hidden. They can be measured. Distant starlight arcs around heavy bodies. Signal travel times shift in the nearness of dense masses. And the very structure of space-time governs the grand outline and future of the universe. It is also vital to recognize that curvature is not confined to one spot. It can travel. A sudden change in mass, two black holes merging, sends a tremor through the fabric. These tremors are gravitational waves, delicate ripples that run outward at light speed, carrying energy and stories across the dark. Their first detection by LIGO in 2015 offered direct evidence not only of black holes, but of space-time's own capacity to quiver and move. A quiet elegance of general relativity is that it banishes action at a distance. In the Newtonian picture, two bodies can reach across emptiness instantly. In relativity, influence moves at a finite speed, never faster than light. Gravity's sway is transmitted by the evolving geometry itself, honoring the speed limit of special relativity and rooting cause and effect within space-time's shape. Time's behavior in curved space-time is another natural consequence of this geometry. In general relativity, time does not flow uniformly. Its tempo depends on gravitational potential, on how deep within a curvature well a clock resides. Closer to mass, a clock ticks more slowly. Farther away, it runs a little faster. This phenomenon, gravitational time dilation, is not merely theoretical. Atomic clocks have confirmed it at different altitudes on Earth, aboard satellites, even on airplanes. In Einstein's description, time is a coordinate that bends and stretches, its gentle pace molded by the surrounding geometry. Space-time geometry also dictates the universe's structure at the widest scales. Applying Einstein's equations to the cosmos as a whole, cosmologists derive models that describe how the universe expands, curves, and evolves. These models predict that space-time can possess global curvature, flat, open, or closed, depending on the total energy density that fills it. Observations of the cosmic microwave background suggest our universe is very nearly flat, though not exactly so. Even then, that flatness is a local trait of the portion we can observe. The full geometry may reach far beyond our horizon. On even larger canvases, space-time geometry frames cosmological inflation, a swift, early expansion that smoothed irregularities and seeded the structures we see today. The subtle geometry of that inflationary moment left marks on the microwave background, tiny ripples in temperature and density fingerprints we still study to learn about our beginnings and our fate. Another striking implication of space-time geometry is that it responds not only to matter, but to energy. This includes dark energy, a mysterious presence suffusing empty space and accelerating the universe's expansion. Dark energy shapes curvature not by drawing masses together, but by acting repulsively on cosmic scales. The discovery of this acceleration in the late 1990 seconds revealed that geometry and energy are bound together, not just nearby, but across the whole of the cosmos. Despite its triumphs, the geometric portrait of gravity raises deep questions. At a black hole's center, theory predicts a singularity where curvature becomes infinite and the familiar rules of general relativity falter. In such extremes, the smooth cloth of space-time may lose its meaning. Physicists suspect a quantum theory of gravity, still undiscovered, will one day replace the classical picture there, exposing a more granular weave to space-time itself. Even so, the geometric vision of general relativity remains unmatched in clarity and grace. It turns gravity into nothing more and nothing less than a reshaping of existence. No hidden forces, no instantaneous reach, only the bending and easing of a living, breathing space-time. Planetary orbits, the arching of light, the passage of time, and the universe's expansion arise naturally from this geometry. Space-time is not merely the arena where physics happens, it is physics in one of its purest forms. And so, as we drift through this invisible design, we are not just passengers on a cosmic journey. We belong to the geometry itself. Each breath, each heartbeat, tilts the curvature around us by the faintest trace, even if we cannot sense it. Everything that exists contributes its quiet presence to space-time's shape. Just as every fold in a sheet is influenced by the creases beside it, there is, in that gentle thought, a kind of existential grace. That even when motion pauses and noise subsides, you are never truly still. You are always held, always woven into something greater, part of the cosmic form that keeps stars, galaxies, and the soft ticking of time. Time, as we live it, feels steady and universal. It moves forward with calm certainty, unaware of our direction or speed, flowing evenly for everyone, everywhere. From our narrow human vantage point, time seems absolute, a heartbeat that never changes pace. But this is an illusion, born from our limited reach and gentle corner of the cosmos. In truth, time is far more fluid. It bends, it stretches, it folds under motion and gravity alike. Through the quiet vision of general relativity, time reveals itself not as a constant stream, but as something alive, woven into the same fabric as space, changing its rhythm wherever the universe curves. The result is a world where seconds are not equal, where time can slow, accelerate, or even open the door to a kind of travel that feels like stepping beyond the edge of experience. The concept of time dilation emerges naturally from this cosmic fabric. It describes how time itself moves at different rates for observers in different gravitational depths or at varying speeds. This isn't poetic exaggeration, it's a measurable, proven fact etched into the structure of reality. Where gravity grows stronger, time slows down. Clocks near massive worlds, burning stars, or black holes accumulate less time than clocks drifting far from such influence. This difference is not the product of malfunction or friction. It is the direct consequence of how mass reshapes space-time itself. To glimpse why, one must remember Einstein's idea that mass tells space-time how to curve. That curve affects not only distance, but also the very texture of time. A clock resting deep in a gravitational valley traces a path through a steeper geometry, marking time more slowly than one perched high above. To someone observing from afar, that clock's ticking appears languid, as though caught in syrup. The deeper the gravitational well, the slower the beat of time within it. And though it may sound like fantasy, this slowing is measurable, even here on Earth. Time dilation is not confined to black holes and distant suns. We have seen it in the quiet tick of atomic clocks carried aboard aircraft, placed atop mountains, or circling the planet in orbit. The global positioning system is perhaps its most elegant demonstration. High above Earth, GPS satellites circle through weaker gravity, their onboard clocks racing ahead by about 45 microseconds every day compared to those on the surface. If left uncorrected, their readings would wander by kilometers, throwing every map into chaos. Engineers account for this difference, a daily act of trust in Einstein's geometry, proving again that relativity is not an abstraction, but a working heartbeat of modern life. Yet beyond the ordinary, time dilation becomes staggering near extreme gravity. Around neutron stars and black holes, time slows almost to stillness. Imagine hovering just above the event horizon of a black hole, not falling in, but suspended, barely outside that point of no return. For someone watching from afar, hours might pass, days even, while for you, only minutes drift by. If you were rescued and pulled back into gentle space, you would find the universe older, loved ones aged, civilizations perhaps changed, while your own body had felt barely a whisper of time. In this sense, gravitational time dilation creates a kind of one-way journey forward through time. You would not have traveled backward, but you would have slipped ahead, a traveler into the future, carried by gravity's soft distortion. Science fiction often paints this idea with wonder and fear, but its foundation is pure physics. No machines or paradoxes required, just gravity, patience, and a willingness to stand on the edge of eternity. Of course, surviving such an environment would be nearly impossible. But the idea itself tells us something profound. Time travel into the future is not only possible, it is, in some corners of the universe, inevitable. There is another way time stretches, not through gravity, but through motion itself. According to special relativity, time slows for objects in motion. The faster one moves, the slower one ages, at least compared to someone at rest. This is called kinematic time dilation. And like its gravitational cousin, it has been tested again and again. In particle accelerators, unstable particles moving near the speed of light live longer than identical ones at rest. Their internal clocks slow, their lifetimes stretch not through magic, but through motion, altering the geometry of their existence. Even the skies above prove this truth. Muons, ghost-like particles born high in Earth's atmosphere, should decay long before reaching the ground. Yet, they do arrive, because their great speed slows their internal time, allowing them to endure the journey. Nature, with quiet precision, obeys Einstein's vision every moment. Gravitational and kinematic time dilation are not separate miracles. They are reflections of the same truth. Both arise from differences in the paths through space-time that each observer follows. Whether motion or gravity creates the change, the cause is geometry, the bending of the fabric itself, and the unique curve each traveler traces within it. When stretched to its extremes, this idea begins to shimmer with wonder. Imagine a civilization orbiting near a black hole's edge, never crossing the horizon. For them, moments might pass while, beyond, stars are born and die, galaxies evolve, and ages fade. The far future of the universe could unfold before their eyes, and they would scarcely age at all. This is not the stuff of myth. The equations themselves allow it. Relativity gives permission for these one-way voyages through time. No law forbids them. Yet, returning is another matter entirely. Gravitational time travel, unlike the dreams of machines and portals, is irreversible. General relativity's equations are symmetric in time, but nature seems to prefer one direction. Some solutions, like Gödel's rotating universe or the strange closed time-like curves, hint at the mathematical possibility of going backward. Yet they demand conditions that strain reality itself, universes that twist, or energies that pull in reverse. Most physicists believe something deep. Perhaps Hawking's chronology protection conjecture forbids such loops from ever forming, keeping causality intact. The forward flow of time remains open, the backward path forever closed. Still, even this forward motion reshapes how we understand ourselves. Time dilation blurs the boundary between physics and philosophy. If two travelers age at different rates, what does it mean to share a moment? What does now even mean when time itself refuses to be absolute? In a relativistic universe, simultaneity dissolves. What is happening now for one observer may already be past or not yet begun for another. Light cones and causal webs define what can touch what, weaving a structure where time flows differently, depending on where and how fast you are. There is no single river of time sweeping us all forward. Instead, the universe is a landscape, a curved, dynamic terrain of time and space intertwined. Every being, every atom, every thought moves along its own winding trail, a personal thread through the cosmic tapestry. Your heartbeat, your breath, your memories, they trace a path through space-time that belongs to no one else. The seconds that cradle you are not the same as those that cradle another. So while time may feel linear, under general relativity, it is flexible, elastic, deeply personal. Each of us is a traveler, drifting not only through the void of space, but through our own private duration, sculpted by gravity and motion alike. It is humbling to realize that time itself, that quiet metronome beneath all things, is not absolute. It bends, stretches, folds softly around us. The ticking of the watch on your wrist is a local truth, a rhythm tuned by your world's gravity and your pace through it. To live is to glide along these invisible contours of time, never perfectly aligned with anyone else. And in that divergence, there is beauty. No two lives, no two moments, no two journeys through space-time are ever identical. Each of us carries our own measure of time, a singular flow through the same great fabric. Yet, somehow, all our paths intertwine, shimmering through the same cosmic field, curved, shifting, and profoundly connected. To understand gravity the way Einstein did, we begin not with distant stars or crowded equations, but with falling. Not the jolt we fear, but a calm, universal descent, the kind that led Galileo to let polished spheres slip from a tower and led Einstein to picture an elevator sliding through the dark. Freefall, so ordinary on Earth, became for Einstein a quiet key, turning in a hidden lock and revealing a deeper pattern of nature. In Newtonian physics, an object in free fall is one that is released and allowed to move under gravity alone. It accelerates downward because a force acts upon it, drawing it toward Earth's center. The strength of that force is proportional to the object's mass and decreases with the square of the distance from the center. This picture carries us through most of life with graceful accuracy. Yet inside its simplicity, a soft strangeness lingers. Different objects, regardless of their mass, descend together. In a vacuum, a feather keeps pace with a bowling ball. In Newton's equations, the mass that resists acceleration and the mass that responds to gravity appear on opposite sides and cancel, leaving the same shared fall. Newton did not explain why this cancellation must hold. It was taken as a faithful fact. Einstein took that familiar observation and listened for a deeper note. He realized that the equality of inertial mass and gravitational mass was not a mere algebraic trick, but a profound clue that pointed beyond forces toward the geometry of the world itself. He tested the clue with a thought experiment. Imagine a sealed elevator, far from all stars and planets. If rockets push the elevator upward with constant acceleration, you feel pressed to the floor. Inside, the sensation is indistinguishable from gravity. Now imagine a second elevator, hovering high above Earth, then released. As it falls, you float. Let a key slip from your fingers, and it lingers beside you. For that brief descent, every part of the system falls together, and the feeling of weight dissolves. Einstein declared these experiences equivalent. This is the equivalence principle. Inside a small, closed room, no local experiment can tell uniform acceleration from free fall in a gravitational field. From this seed he grew a new vision of gravity, not as a force reaching across emptiness, but as a property of space-time itself, the shape that guides all motion. In this vision, a dropped object does not speed up because something pulls. It simply follows a natural path, a geodesic through curved space-time. If released and untouched, it travels the straightest route the geometry allows. You perceive it as falling only because you are not in free fall. Standing on Earth, the ground exerts an upward push, forcing you away from the geodesic your body would otherwise choose. Gravity, in this language, is not a hand dragging things downward. Surfaces are what nudge objects away from their natural lines. The reversal feels strange at first, but it matches experience. Astronauts in orbit feel weightless, not because gravity vanishes, but because they and their ship are always falling around Earth, tracing the same gentle curve together. The equivalence principle has been tested with extraordinary care. Physicists have dropped objects of different composition in vacuum, compared clocks in free fall with clocks at rest, and flown satellites that shelter test masses from other forces. Again and again, the results return the same refrain. When only gravity acts, all bodies fall identically. Even quantum experiments using atomic interferometry confirm the principle on microscopic scales, where matter behaves like waves and still obeys the shared descent. These successes sharpen Einstein's insight. Gravity is less about forces acting on things than about the shapes of the paths they take. With this understanding, he extended special relativity, which governs uniform motion, into a broader framework that embraces acceleration and gravity. The flat, rigid geometry of special relativity became the dynamic, curved geometry of general relativity. Free fall, then, is not merely a mode of motion. It is a keyhole through which we glimpse how space-time responds to mass and energy. When Einstein presented his field equations in 1915, puzzles that had lingered for decades found their place. The small excess precession of Mercury's orbit, stubborn under Newton's law, arose naturally from the sun's curved space-time. Light bending near the sun, the slowing of time close to massive bodies, the fierce choreography of black holes, all followed from one elegant idea: that falling can be indistinguishable from floating, and that acceleration and gravity are two faces of a single geometry. The power of the equivalence principle lies in its local promise. It does not claim to describe gravity everywhere at once. It speaks about small regions where curvature can be neglected or treated as uniform. In such neighborhoods, the laws of physics take the form of special relativity. Light travels in straight lines, clocks tick steadily, and freely falling objects move uniformly, as though in a little patch of flat space carved out of a larger, curved world. There is, however, a gentle caveat woven into the principle. It is strictly local. In a sufficiently small elevator, gravity and acceleration cannot be told apart. Enlarge the cabin, and the difference begins to whisper through what physicists call tidal effects. Two raindrops, released side by side, drift together in a tiny room. Scale the room up, and you notice them slowly converging or separating, because Earth's field is not perfectly uniform. That subtle shearing is curvature announcing itself, the same quiet influence that lifts ocean tides and stretches comets near planets. The equivalence holds perfectly in small rooms, where the field is nearly constant. As the room grows, the unevenness of gravity's grip reveals the underlying curve. Only when we compare different regions, places where curvature changes, do the felt effects of gravity emerge in full. In this sense, general relativity is a quilt of locally flat patches stitched together by curvature. Even time is part of the quilt. A clock in free fall does not tick slowly because it falls. It keeps its proper time along its geodesic. Differences appear only when we compare it to a clock held off the geodesic by the steady press of a surface. Gravity does not seize time directly. It shapes the paths through which time flows. This, too, recasts what it means to be still. On Earth, the heaviness we call weight is the ground preventing our fall. From the viewpoint of general relativity, we are the ones accelerating upward relative to a freely falling frame, feeling the push that keeps us from our natural line. An orbiting satellite, by contrast, is unforced. It coasts along its geodesic, feeling no weight at all. We on the ground are the ones deviating from freedom. The idea can be unsettling. Habit tells us we are motionless, anchored by gravity. Space-time tells us the satellite is the one at ease, while we are gently, constantly turned aside from our preferred path. Gravity does not pull. Geometry guides. Resist that guidance, and weight appears. The reach of the equivalence principle extends into other corners of physics, inspiring attempts to braid gravity with quantum theory. Some approaches, entropic gravity, holographic duality, imagine space-time and gravity as emergent, rising from information, thermodynamics, or entanglement, as if geometry were a tapestry woven from countless microscopic threads. None of these proposals supplants general relativity, yet each is animated by Einstein's central thought. The essence of gravity is bound to how we experience motion and acceleration. At the heart of it all is a simple recognition: to fall freely is to float. To let go is to return to the path the universe quietly prepared. What we once called force becomes a whisper etched into space and time. And so, each time an object slips from your hand and drops, you witness not a pull, but a path, an ancient trajectory inscribed in the curves of the world, a line that was waiting even before the motion began. The object is not being captured, it is being released. It returns to the route that has always awaited it. Perhaps we are doing the same, moving through a universe that bends around us, unaware of the deeper pattern beneath our feet. And in that shared falling, we are not alone. We belong to a pattern, an unfolding, a geometry written long before we learned how to look, held softly by the same silent grace that guides stars, carries oceans, and keeps the quiet ticking of time. Motion through space has always seemed simple to the human mind. Since the first eyes looked up at wandering stars, we have imagined a universe of clear, predictable lines where things move straight unless pushed, and every curve demands a cause. From Newton's hand came laws that painted this simplicity in firm strokes. If undisturbed, an object travels straight, and if it bends, some invisible hand must be pulling. For centuries, this vision shaped the way we thought about the heavens: planets circling under the steady pull of gravity, orbits born from perfect balances of motion and force. But Einstein's general relativity changed the melody. It replaced mechanics with geometry, force with form. Objects do not move because they are pushed or pulled. They move because they follow the hidden architecture of space-time itself. A planet dancing around a star, a comet tracing its long ellipse, even a silent spacecraft drifting between worlds, none are truly pulled from their course. They are gliding through a curved universe, tracing the straightest possible lines within a geometry that itself is bent. Their motion is poetry, written in the shape of space-time. In this new language, a straight line becomes a geodesic, the path that a freely falling object follows when untouched by any other force. In flat space-time, a geodesic is exactly the straight line of Euclidean thought. But where mass and energy reside, space-time bends, and the geodesic turns into a graceful curve, a looping rhythm that looks like motion under influence, but is simply the shape of freedom. The curvature belongs not to the traveler, but to the landscape through which it moves. Picture a smooth rubber sheet, stretched taut. Roll a marble across it, and it glides straight. Place a heavy ball in the center, the sheet dips, and when the marble rolls again, it curves toward the depression. No sideways force touches it. It simply follows the easiest path, the path the surface itself has drawn. That humble analogy captures the heart of general relativity. Gravity is not a force, it is the shape of the terrain. Mass bends the geometry of space-time, and objects respond by following those curves. In our real universe, that landscape unfolds not in 2 dimensions, but in 4, 3 of space, 1 of time. The curvature is written by the metric tensor, a mathematical symphony describing how distances and durations behave at every point. Introduce mass or energy, and the curvature changes. The geodesics adjust, like rivers finding new beds after rain. A star does not tug on a planet. It reshapes the space-time around it, and the planet follows that geometry. The orbit of Mercury, long an astronomical puzzle, proved this truth. For centuries, observers noted that Mercury's ellipse precessed slightly, refusing to close neatly. Newton's laws explained most of the motion, but not that stubborn sliver of difference. Then, Einstein turned his field equations toward the Sunday, when he accounted for the way space-time curved near its blazing mass. The extra precession appeared naturally. No mysterious forces, no unseen planets, just geometry. The riddle dissolved into the fabric of space itself. It was the first great victory of relativity, proof that what seemed like an irregular orbit was in fact the purest motion through curved space-time. Light, too, bends. Though photons have no mass, they still follow geodesics, called null geodesics, the straightest possible routes through curved space and time. When light brushes past a star, its path arcs gently, not because the star tugs upon it, but because the geometry through which it travels has changed shape. In 1919, during a total solar eclipse, this bending of starlight was seen. As sunlight dimmed, stars near the darkened edge of the sun appeared displaced, just as Einstein's equations foretold. It was as if the sun had quietly curved the space around it, and light, ever obedient, followed the curve. With that observation, the world glimpsed that even radiance is guided by gravity's geometry. Yet the story does not end with single orbits or solitary rays. The shape of space-time determines the motion of everything from the spiraling arms of galaxies to the clusters that bind them, to the very expansion of the cosmos. General relativity reveals that motion is not about pushing or pulling, but about the universe itself guiding matter along invisible rails of geometry. On the largest scales, space-time may not be flat at all. The cosmos could be round like a sphere, curved outward like a saddle, or perfectly balanced and flat. The difference depends on how much mass and energy fill it. Each possibility carries its own destiny. A universe that closes in on itself, one that expands forever, or one that hovers on the edge of both. Measurements of the cosmic microwave background suggest our universe is almost flat, a vast level ocean stretching in all directions. Yet even a nearly flat cosmos hides small curvatures where galaxies gather and dark matter weaves invisible webs. Local curvature rules our daily experience, while global curvature whispers the fate of all things. That local bending reveals itself most dramatically in gravitational lensing. As light from distant galaxies travels through space-time shaped by intervening masses, it bends and splits, forming arcs, rings, and ghostly echoes. These are not tricks of the telescope, but the natural artistry of curved geometry. The cosmos itself becomes a lens, sculpting light into cosmic mandalas that carry the signature of space-time's shape. One of the strangest insights of relativity is that objects at rest are not truly free. A rock resting on the ground is not following a geodesic. It is held back by the upward push of the earth beneath it. The ground interrupts its natural path. You, standing still, feel weight, precisely because you are prevented from falling along your geodesic. By contrast, an orbiting satellite is free. Though it appears to curve endlessly around Earth, it is not forced. It glides effortlessly along a geodesic, obeying only the shape of space-time. What looks like acceleration is actually the simplest motion possible in a curved geometry. In Einstein's world, orbits are not struggles between competing forces. They are the straightest lines the universe allows. Even falling itself changes meaning. Objects fall not because the Earth pulls them, but because their natural paths dip inward through curved space-time. The ground beneath your feet keeps you from continuing on that route, and that resistance, that deviation from the geometry of freedom, is what you call weight. Gravity, in this light is not an interaction, but an interruption. The mathematics behind this picture is intricate but harmonious. Tensors, connections, curvature, scalars, they sound abstract, yet they describe the living structure of reality. The Riemann curvature tensor quantifies exactly how space-time bends under the presence of energy, linking the pattern of motion to the fabric's strain. Einstein's field equations tie this curvature directly to the stress-energy tensor, the accounting of all matter and energy in existence. The result is profound. Motion arises from curvature, and curvature arises from content. What moves through space-time and what shapes it are two sides of the same dialogue. Planets, light, even the empty vacuum participate in this quiet exchange. This geometric language extends far beyond astronomy. Time itself bends and flows according to the path an observer follows through the curved universe. Each clock, each rhythm, each heartbeat measures not a universal tempo but a personal journey along its geodesic. Time and motion are not external forces imposed upon us. They are the echoes of geometry itself. The beauty of general relativity lies not only in its precision but in its unity. Gravitational waves, for instance, are not invisible energies traveling through space. They are ripples of space, the undulation of space-time's geometry as massive bodies collide or spiral together. Detected a century after Einstein predicted them, these waves stretch and squeeze distances as they pass, not by pulling objects directly but by altering the shape through which those objects move. Even in this complexity, the core idea remains disarmingly simple. Mass and energy curve spacetime. Curved spacetime tells matter how to move. The universe's every orbit, every expansion, every subtle drift is born from this partnership between matter and geometry. Nothing in this picture is truly still. Even an isolated object floating in deep space participates in the greater curvature, both shaping and being shaped by it. Its motion is not random, not lonely, but a conversation with the whole cosmos. And perhaps that is the most serene truth hidden in Einstein's equations, that every motion, every orbit, every fall is not separation, but connection. The curve of your path is written by the stars. The rhythm of your time is guided by galaxies. Each step you take, each moment that passes, is a quiet dialogue with the geometry of the universe, a reminder that to move, to exist, to fall, is to belong. For much of human history, light felt like the universe's pure straight edge, the swiftest, most unbothered traveler, immune to tug or touch. In the Newtonian view, gravity, addressed only the massive, weightless light, should pass through the cosmos unchanged, an untouchable surveyor of the night. But general relativity remade that intuition. Gravity, Einstein said, is not a force that reaches out. It is geometry, the very shape of space-time. Light does not float across some passive stage. It moves within the stage itself, responding to every curve and fold of the fabric it crosses. And when space-time bends under the presence of mass or energy, the path of light must bend as well. This is not gravity pulling on photons in the old sense. It is space-time guiding them. Light forever runs along null geodesics, the natural tracks laid down for massless travelers by the curvature of space-time. Viewed only in space, these geodesics can look bowed or twisted. From that vision sprang a bold prediction: starlight, grazing a massive body like the sun, would be displaced, the star's apparent position shifting in the sky. In 1919, during a total solar eclipse, Arthur Eddington and his colleagues listened to that prediction with their instruments. They found what Einstein's equations promised. Starlight skimming the sun was deflected by just the right amount. It was the theory's first public triumph, and from that moment, light itself became a messenger of geometry rather than a symbol of immunity. Yet, light's bending is not an eclipse-only trick. Throughout the universe, at every scale, mass reshapes the routes that photons choose. Galaxies and clusters become gravitational lenses, magnifying and distorting the light of more distant sources behind them. In rare alignments, the result is an Einstein ring, a bright, nearly perfect circle. More often, the outcome is subtler, doubled or tripled images of the same object, faint arcs stretched like glasswork across the sky, or ghostly repeats where light has taken several curved routes to arrive. This lensing is now one of cosmology's sharpest tools. It lets us study otherwise invisible structures, galaxies too dim or far to resolve directly by amplifying their light. It also reveals dark matter, a form of matter that neither glows nor absorbs, yet sculpts space-time. We cannot see dark matter itself, but we can map it by reading the way it bends the paths of photons. On still larger canvases, lensing brushes the cosmic microwave background, the faded afterglow of the Big Bang. Traveling for billions of years, those ancient photons are nudged by the patchwork of gravity wells they pass. The nudge is gentle, but it imprints delicate changes in temperature and polarization, a fingerprint of structure spread across the sky. By measuring those tiny distortions, cosmologists trace how matter clumped and stretched, infer the push of dark energy, and test the very shape and stiffness of spacetime. In this way, the oldest light becomes a living map of everything it crossed. Curvature also changes light's color. Climbing out of a gravity well, a photon keeps its speed but surrenders energy by stretching its wavelength. This gravitational redshift moves light toward the red, a quiet, measurable slide predicted by general relativity and observed both in laboratories and among the stars. Light from a white dwarf's surface shows this shift, its spectrum tugged redward by the star's intense gravity. Near a black hole, the effect becomes extreme. Escaping light is stretched so drastically that to faraway eyes it fades toward invisibility, giving the event horizon its defining silence. Redshift is more than a curiosity. Our satellites feel it. The clocks aboard GPS spacecraft tick in a gentler gravitational field than clocks on Earth's surface, and their signals carry the imprint of both general and special relativity. Engineers must correct for those relativistic shifts to keep positions precise on our maps. Without those daily corrections, navigation would drift into chaos within hours. In this sense, every route you plot is quietly balanced on Einstein's equations. Another grace of curved space-time is the gravitational time delay, or Shapiro delay. Light sliding near a mass not only curves, it takes longer to complete its journey. The geometry near mass is stretched compared to flat space, so even if the spatial separation is unchanged, the time between points grows. We have measured this with radar bounced off planets. When the beam threads close to the sun, its return arrives later than a flat world clock would promise, and the delay matches relativity's calculations with beautiful accuracy. The universe, it seems, pads the schedule where space is deepened by gravity. Time delay appears on grander stages as well. A lensed quasar or supernova can send us multiple images along different geodesics. Each path runs through a different landscape of curvature, so the light reaches us at different moments. Sometimes we watch the same explosion twice or thrice, separated by days or years, echoes traveling around a cosmic obstacle. Those staggered arrivals help measure the universe's expansion and test gravity under distant, extreme conditions. Even gravitational waves, ripples in space-time, stirred by massive, accelerating bodies, converse with light in ways we can detect. When such a wave passes, it stretches one direction of space while squeezing the perpendicular. In detectors like LIGO, laser beams run down two long arms and back. As the wave rolls by, the arms change length ever so slightly. The returning beams recombine out of step, carving a pattern that whispers of the wave's passing, not because the light misbehaves, but because the space it traveled was briefly rewritten. This meeting of light and geometry makes photons perfect couriers. Each beam carries memories of the terrain it crossed, every bend, every delay, every shift. Light is not merely illumination. It is a probe, an explorer, an archivist, quietly collecting the contours of space-time and delivering them to our telescopes. Black holes stage this interplay at its most dramatic. Near them, curvature grows so intense that light can be trapped in orbit. There exists the photon sphere, a region where a photon, flung at just the right angle, can circle the hole again and again. A tiny nudge, and the photon either spirals inward across the horizon or escapes to tell the tale. The photon sphere shapes the shadow seen by the Event Horizon Telescope in M87, outlining absence with the glow of captured light. Some rays skim the sphere once, others loop several times before escaping, producing a nested sequence of images, each dimmer, more delayed, more distorted. These layers encode an intricate map of the black hole's geometry, a fingerprint pressed by gravity into light. Even far from such extremes, gravity and light recast our view of the cosmos. As the universe expands, distant galaxies look cosmologically redshifted, their wavelengths stretched by the growth of space itself. This redshift differs from the gravitational kind but tells its own story. By measuring it, astronomers chart how fast the fabric expands and reconstruct a history of cosmic growth. Together, these effects, bending, redshift, delay, and lensing, transform our understanding of light from passive traveler to active participant. Photons do not merely cross spacetime, they respond to it, remember it, and relay it back to us. Every star we admire, every galaxy we catalog, every flare we catch from the deep past reaches us along a path braided by gravity, a path that reveals the landscape it traversed. And still, despite the twists and detours, light is faithful. It crosses uncountable distances and untold ages to arrive with messages intact, echoes of beginnings, outlines of the unreachable, evidence of spacetime's very form. Light teaches us not only to see, it teaches us to know by carrying the imprint of geometry across the dark. Perhaps then, the bending of light is more than proof of gravity's reach. It is a gentle reminder that even the straightest thing we can name, the photon's path, yields to the shape of reality, and in yielding, shows us the hidden ties that bind all things together. Among all the predictions of general relativity, few feel as startling, as extreme, or as beautifully counterintuitive as the black hole. In Einstein's equations, black holes are not contrivances or indulgent fantasies. They emerge as natural, unavoidable shapes in the geometry regions where space-time is no longer gently bowed, but folded so intensely that every path leans inward, and nothing, not even light, can make its way back out. Hints of such darkness appeared long before Einstein. In the late 18th century, Jean Michel and Pierre-Simon Laplace wondered whether a body might be so massive that its escape velocity would exceed the speed of light. Without a modern theory of light or a relativistic frame to hold the thought, their ideas fluttered as curiosities and fell quiet. Then, in 1916, Carl Schwarzschild offered the first exact solution to Einstein's new field equations for a non-rotating, spherically symmetric mass. Inside that solution lay a critical radius, the Schwarzschild radius, beyond which the curvature of space-time grows so severe that all geodesics, whether traced by particles or photons, stream inward. The boundary defined by that radius is the event horizon. It is not a surface with texture or substance. It carries no skin. It is a one-way threshold. Cross it, and no signal, no influence, no memory can return to the outside. From the vantage of general relativity, the horizon is the edge beyond which external prediction ends. We can calculate what the outside sees, but not what can ever be seen from within. What lives inside that boundary remains a matter of inference and restraint. Classical general relativity says, collapse continues, squeezing matter into a point, a singularity where curvature climbs to infinity, and tidal forces stretch and crush without limit. Such infinities likely mark the limits of the theory itself, a sign that quantum gravity must one day smooth the fabric at the smallest scales. But for now, we know this much. Once a horizon forms, no known mechanism can undo it. Black holes, for all their ferocity, are among the universe's most stable, persistent entities. And they are real, not ghost stories, but astrophysical citizens. They take shape as massive stars end their nuclear lives. When fusion embers fade, a star can no longer prop itself against its own weight. If the remaining core is heavy enough, no pressure, not the quantum stiffness that saves white dwarfs, nor the degeneracy that steadies neutron stars can halt collapse. The result is a stellar mass black hole, often several suns gathered into a shadowed region only a few kilometers wide. For a long time, we thought such objects could only be traced indirectly by what they do to matter nearby, but our techniques have sharpened. One of the clearest signatures is the accretion disk, a whirl of gas and dust spiraling inward, heated by friction and compression until it shines fiercely, especially in X-rays. Space telescopes, such as Chandra and XMM Newton, watch these luminous storms, making black holes visible even when their horizons themselves remain forever unseen. Another voice reached us in 2015, the tremor of gravitational waves. As two black holes circle and merge, they wrinkle space-time, sending ripples outward at light speed. LIGO's first detection opened a new sense for astronomy, carrying the mass, spin, and distance of colliding holes in the fine structure of the wave. Where light can be blocked, bent, or lost, these waves pass cleanly, telling us of dark, dynamic processes otherwise hidden. Then, in 2019, we saw a different kind of portrait, the Event Horizon Telescope's image of the supermassive black hole in M87. Not a snapshot of the void itself, but of its shadow, a dark center encircled by a ring of light from hot gas just outside the horizon, bent and brightened by intense gravitational lensing. The size and shape of that ring matched predictions etched decades before, a quiet confirmation that even at the brink of the unknowable, geometry remains faithful to its equations. Black holes span a wide range of scales. Some weigh a handful of suns, others, supermassive black holes, rest in the hearts of galaxies, with millions or billions of solar masses gathered into a single curve of space-time. How such giants first formed remains an open question. Perhaps they were seeded by the collapse of pristine, massive clouds in the early universe. Perhaps they grew by steady feasting and mergers, one dark heart swallowing another over cosmic time. Whatever their beginning, they shaped their host galaxies by swallowing matter, by launching collimated jets, by stirring and warming the gas from which stars are born. When a supermassive black hole feeds rapidly, the center of the galaxy flares into an active galactic nucleus, AGN. From far away, we see these as quasars, beacons that outshine entire galaxies, powered by the conversion of gravitational potential energy into heat and radiation, as in falling matter roils to extreme temperatures. Because many quasars lie far across space and time, they become time machines of a sort, letting us probe the young universe, its ingredients, its structure, its restless growth. Near a horizon, physics strains the edges of understanding, not only in gravity, but in information and entropy. In the 1,970 seconds, Stephen Hawking found that black holes are not perfectly black. Quantum fields in curved space-time tint the horizon with a faint Hawking radiation, a thermal whisper that, over unimaginable ages, lets a black hole lose mass and slowly evaporate. For astrophysical holes, this glow is too weak to catch with present eyes, yet its implications are thunderous. If evaporation proceeds and the radiation carries no imprint of what fell in, information seems to be lost, a violation of quantum mechanics' most cherished bookkeeping rule. This black hole information paradox has stirred a generation of ideas, holographic principles that paint the contents of a volume on its boundary, entanglement that stretches across the horizon, quantum extremal surfaces and islands where information might hide in plain sight. We do not yet have a final answer, but the paradox serves as a compass, pointing toward a theory where gravity and quantum law share a single map. Even outside quantum debates, time itself behaves strangely near a horizon. To a distant observer, an object falling toward the boundary appears to slow, its signals redshifting, its clocks stretching, until it seems to hover and fade at the edge. To the falling traveler, there is no such pause. They cross the horizon in a finite heartbeat without noticing any local drama. Both descriptions are true within their frames. The discrepancy is not illusion, but geometry. The horizon is a divider of causal worlds. What lies within can no longer send news to the outside. General relativity allows black holes with richer identities than mere mass. The Kerr solution describes a rotating black hole, and rotation begets an ergosphere, a region outside the horizon, where space-time is dragged so strongly that no object can remain at rest relative to the distant stars. Within this whirling domain, energy can, in principle, be extracted. The Penrose process imagines splitting a particle's path so that one fragment falls in with negative energy relative to infinity, letting the other escape with more energy than it brought. In astrophysics, magnetic fields and plasma flows may perform a similar theft, powering jets that lance from galactic cores. Some mathematical extensions even admit more exotic corridors, wormholes, tunnels that join distant regions of spacetime. But the price for such passages is steep. Forms of matter with properties not known to nature, violations of energy conditions that our best tested theories hold dear. For now, wormholes rest in the cabinet of beautiful possibilities, awaiting the physics that might one day grant or deny them. Despite the speculation that surrounds their edges, the center of the subject is sure. Black holes are not fiction. They are observed, weighed, imaged in silhouette, and heard in gravitational song. They serve as laboratories where our theories are stretched to breaking, where we test how light moves when even light struggles, how time flows as time thins, how information behaves at the lip of forever. Their formation, feeding, and fusing sculpt galaxies. Their mergers send waves that tremble across the universe. Their accretion lights quasars that mark the dawn of structure. They also define boundaries, literal and conceptual horizons beyond which observation cannot follow, questions that cannot be answered from the outside. Yet those boundaries are not the end of curiosity. They are invitations to refine our laws, to draw better maps, to listen more carefully. Perhaps the allure of black holes is not only their power or mystery, but their precision. They obey the rules with a stern elegance: mass, spin, charge, horizon, area, and temperature. The delicate accounting that links geometry to thermodynamics. They are the universe's firmest therefores, the logical extreme of what happens when gravity is allowed to complete its sentence. And still, in their quiet, they speak. They tell us that nature does not fear extremes, that the fabric of reality can stretch and fold and collapse and still hold a deeper order. They tell us that even where no light returns, something essential remains: the marriage of geometry and motion, of energy and space, of time and its limits. Stand beneath the night and imagine that distant darkness, not empty, not chaotic, but exact. Around it, matter swirls and glows. Within it, equations meet their horizon. Between those two realms, the ring of light and the ring of silence, we learn how far understanding can go and where it must pause and listen. In that pause, the universe hums softly, and we, small and curious, lean closer to the edge of knowing, where the curve grows deep and the stories of space-time turn into whispers beyond return. In Einstein's great tapestry of general relativity, mass and energy do not merely reside in space-time, they shape it, and that shape, in turn, tells matter and light how to move. For a long time after the theory appeared, scientists saw this interplay as serene and static, the steady curvature around a planet, the quiet well of a star's gravity. But hidden in the mathematics was a hint of motion, a subtle pulse. If space-time could curve, then surely it could ripple. And if those ripples could travel, then gravity itself might carry energy outward, like light does, but not through space, rather as space. These undulations came to be called gravitational waves. They are not waves moving through a medium. They are waves of the medium, the very stretching and compressing of distance and time themselves. When one passes, nothing is pushed or pulled in the ordinary sense. Instead, space-time briefly swells and shrinks, subtly altering how far apart things are. Though nothing moves, they are delicate beyond imagining. Yet, they are among the universe's purest messengers, passing through dust, gas, and light alike, unscattered and unchanged. Where photons can blur or fade, gravitational waves glide untouched, carrying the raw signature of the cosmic upheavals that gave them birth. Einstein first glimpsed their existence in 1916, just a year after completing his theory. The equations made them inevitable. Yet he himself wondered whether they were truly real or just mathematical illusions, ripples of coordinates, not of physics. For decades, physicists debated the question: were these waves tangible or merely the ghostly byproducts of the equation's flexibility? Even if they were real, could they ever be strong enough for humans to detect? To make gravitational waves, mass must accelerate, but not in simple symmetry. A single star pulsating evenly or a planet orbiting perfectly alone cannot radiate them. Gravity, unlike electromagnetism, has no dipole radiation. It needs a quadrupole dance motion with changing asymmetry. Two orbiting bodies, their fields weaving around one another, fit the rhythm perfectly. As they spin, they disturb space-time itself, sending ripples outward. The faster and heavier the partners, the louder the song. The grandest waves come from cataclysms, black holes colliding, neutron stars smashing together, or the core of a dying star imploding under its own weight. For decades, such symphonies could only be inferred, not heard. Then, in 1974, came a clue. The Hulse-Taylor binary pulsar. Two neutron stars locked in orbit, flashing radio pulses with clock-like precision. Over years of patient listening, astronomers saw their orbit shrink ever so slightly. The rate of that decay matched perfectly with Einstein's prediction for energy carried away by gravitational waves. It was the first indirect proof that these ripples were real, and for it, Hulse and Taylor earned the Nobel Prize. Still, no one had yet felt the waves themselves. That silence ended a century after Einstein's prediction. On the 14th of September 2015, the Laser Interferometer Gravitational Wave Observatory recorded a tiny, fleeting tremor in the fabric of existence. Two detectors, one in Louisiana, one in Washington, caught the same whisper, a pattern of stretching and squeezing that matched the theoretical signature of two black holes merging over 1 billion light-years away. In less than half a second, those black holes fused, releasing energy for an instant greater than that of every star shining in the observable universe. By the time the wave reached Earth, its effect was almost unspeakably small, changing the length of LIGO's 4-kilometer arms by a distance less than 1,000th of a proton's width. LIGO detects such ripples using laser interferometry, a method both elegant and daunting. A laser beam is split and sent down two perpendicular tunnels, reflected by mirrors, and brought back to overlap. When a gravitational wave passes, one arm stretches while the other shortens, ever so slightly, creating a tiny interference shift in the light. To isolate that signal, every tremor of Earth, earthquakes, traffic, even the random jitter of atoms must be hushed, cancelled, and silenced. Yet when the pattern emerges, delicate and distinct, it speaks of distant motion, two black holes locked in their last waltz, circling faster and faster until their horizons merge into one. Each oscillation in the signal mirrors a turn in their dance. The final crescendo marks the instant of union. Since that first detection, dozens more events have been captured: black hole mergers, neutron star collisions, even hybrid encounters between the two. Each one has expanded our understanding of stellar life and death, of how the universe builds and recycles its heaviest elements. In 2017, a particular event, GW 170817, brought a revelation. Two neutron stars collided, their crash not only ringing space-time, but shining across every wavelength. Telescopes turned to the source and saw light fading through color's gamma rays, visible glow, radio echoes, revealing the birth of gold, platinum, and other heavy elements forged in that instant. For the first time, we both heard and saw the same cosmic event. It was the dawn of multi-messenger astronomy, a symphony where light and gravity perform together. Gravitational waves have become a new kind of test for general relativity. Every signal carries structure, its frequency rising as orbits tighten, its amplitude swelling before the merge. These shapes can be read like fingerprints, checking whether nature truly follows Einstein's script. So far, every note has matched the score. No deviations, no contradictions. Still, the search continues, because even the slightest discord could reveal physics beyond relativity, a hint of the quantum depths where gravity and space-time dissolve into one another. To find such subtleties, the instruments themselves are evolving. LIGO and Virgo in Italy have been refined to greater sensitivity. Kagra in Japan adds fresh ears deep within its mountain shelter. Plans for the Einstein telescope in Europe promise yet deeper quiet, but the most ambitious ear of all will listen not from Earth, but from space. The Laser Interferometer Space Antenna, a mission of the European Space Agency planned for the 2030 seconds, will stretch its arms across millions of kilometers. 3 spacecraft forming a vast equilateral triangle orbiting the Sunday. LISA will hear lower frequencies than any ground instrument can, gravitational waves, with periods of hours or days born from slow cosmic giants, supermassive black hole mergers, compact binaries, and perhaps whispers from the very dawn of time. At the farthest edge of imagination lies the gravitational wave background, a faint, omnipresent hum created by countless unresolved sources, or perhaps by the primal turbulence of the early universe itself. Detecting that background would be like catching the echo of creation. Networks of pulsars, tiny cosmic clocks, are already listening. Their steady radio pulses, arriving with exquisite regularity, can reveal passing gravitational waves through correlated delays. Recent hints suggest the background may already be brushing against our instruments, waiting to be confirmed. What makes gravitational waves so extraordinary is not just their discovery, but their perspective. For centuries, astronomy was visual. Then it became electromagnetic. Now it has become tactile. We do not simply see the universe, we feel it. These waves do not compete with light. They complement it, adding depth to our senses. They let us perceive what light cannot reach, the hidden mergers cloaked in dust, the dark collisions that emit no glow. It is, in the truest sense, like hearing the cosmos for the first time. These signals were always flowing through us, through the Earth, through our atoms, but we did not yet know how to listen. Now that we can, every detection feels intimate. Each waveform is a story etched in space-time, a record of motion, of orbit, of collapse. Light tells us what something looks like. Gravitational waves tell us how it moved. They do not reflect or scatter. They arrive direct, carrying the very rhythm of the event that made them unedited by the medium they pass through. When a black hole merger from before Earth's first sunrise trembles our detectors, it is as if time itself reaches back to greet us. In the years to come, these ripples may help us answer deeper riddles. They may reveal how matter behaves at nuclear density, how neutron stars hold their structure before they yield. They might whisper clues about dark matter, if unseen compact objects join the dance. And, perhaps, they could guide us toward the long-sought unification of relativity and quantum theory, showing where the smooth fabric of space-time begins to fray. Gravitational waves are quiet beyond words. They carry no light, no color, no scent. They pass without resistance, shifting the universe's geometry by a breath, then continuing on forever. But within that breath is a story of colossal motion, stars dying, black holes merging, the early universe trembling, as it learned its own laws. They are silent messengers, yet they speak profoundly. They remind us that the universe does not communicate only in brilliance or heat. Sometimes it murmurs. And if we become still enough, if our instruments, and perhaps our hearts, can learn to listen, we can feel reality itself moving, softly, through us. A theory only earns our trust when its predictions meet the world and the world nods back. When Albert Einstein released general relativity in 1915, he offered not just a new story about gravity, but a gentle reweaving of space, time, and the geometry that holds them. It was beautiful, yes, but beauty alone does not make truth. Graceful mathematics and a tempting philosophy are beginnings, not endings. Einstein's ideas carried clear promises: how light would bend, how planets would wander, how clocks would keep their secrets, how gravity's influence would travel. Over the next century, those promises would be tested again and again, one of the most careful, far-reaching examinations in all of science. The first famous moment arrived in 1919. Einstein had said that starlight skimming past the sun would not run straight but would slide along curved space-time, appearing shifted to our eyes, not because the sun grabbed photons, but because it shaped the path they must take. During a total solar eclipse, Arthur Eddington's teams took careful photographs of stars near the darkened Sunday. With the sun's glare briefly veiled, the stars seemed to step outward from their usual positions. The measured deflection matched Einstein's numbers, and in that quiet alignment between sky and equation, the theory moved from chalkboard to reality. It was only the first step. Another early victory had been waiting in Mercury's orbit. For generations, astronomers had wrestled with a small, stubborn twist. Mercury's perihelion, the point nearest the sun, crept forward with each circuit. Most of the shift bowed to Newton's laws and the tug of other planets, but not all. About 43 arcseconds per century refused to be explained away. When Einstein mapped the sun's curved space-time and traced Mercury's path within it, the leftover drift dissolved. The theory did not merely fit, it predicted the exact excess. A puzzle turned into a signature, precise and calm. Another essential test reached into time itself. One of Einstein's boldest claims was that time does not flow evenly everywhere. Where gravity is stronger, time softens and slows. Where it is weaker, time runs a little freer. In 1960, the Pound-Rebka experiment listened for this difference. Gamma rays sent from the top of a tower and caught below, where Earth's gravity is slightly deeper, arrived with a tiny shift just as the equations foretold a proof that even over meters, time's pace can change. Later work sharpened the picture further. Atomic clocks flown in airplanes or carried to mountaintops ticked differently than twins kept at sea level. Our global positioning system, a net of satellites circling high above, must balance the influences of both special and general relativity. Up there, clocks tick faster in the gentler gravity. Ignore those nanosecond adjustments, and the maps on our phones would drift by kilometers each day. That such everyday accuracy rests upon relativity is its own kind of quiet wonder. Beyond Earth, binary pulsars, neutron stars in close, relentless orbits offered tests in stronger fields. The Hulse-Taylor pulsar, found in 1974, allowed astronomers to watch an orbit shrink as energy leaked away in gravitational waves. The rate matched relativity's prediction with exquisite fidelity, a powerful, indirect proof that space-time can carry energy in ripples. Over the years, new binary pulsars joined the catalog, and each one sang the same tune. Meanwhile, light itself became both a canvas and a probe. Gravitational lensing, the bending of light by mass, appeared everywhere, from individual galaxies to colossal clusters, forming arcs, rings, and doubled or tripled images. Simulations built on Einstein's equations reproduced these shapes in detail. When the background sources flickered with their own rhythms, the lensed images echoed with slight delays. Those time delays, like fingerprints of geometry, tested the theory across cosmic distances. A striking vision came in 2019. By linking radio dishes worldwide, astronomers fashioned the Event Horizon Telescope, an Earth-sized eye peering at space-time's edge. The image of M87's supermassive black hole showed a bright, asymmetric ring around a deep shadow, exactly the silhouette long predicted. Its size and shape, and the lensing that carved it, matched models drawn from general relativity, demonstrating that even at the brink of a horizon, the equations hold their line. Then came the era of listening to gravity itself. In 2015, LIGO's first detection of a gravitational wave was not just a curious signal, but the living record of two black holes spiraling together. The waveform, the pitch rising, the amplitude swelling matched numerical solutions of Einstein's field equations. Since then, dozens of such events have arrived, each one a new lens on gravity's behavior. Neutron star mergers, in particular, offered a duet of messengers. We heard the space-time ripples and saw the light gamma rays, optical afterglows, radio whispers arriving from the same collision. Across these tests, from atomic seconds to galactic silhouettes, the results have held steady. General relativity keeps passing. Yet physicists do not treat success as a final resting place. They seek edges where the pattern might fray, not out of disbelief, but out of hope for deeper understanding. The theory, magnificent as it is, carries no quantum structure. Near singularities, or in the universe's first moments, quantum gravity should take the stage. General relativity is classical and knows nothing of it. Bridging that divide is one of science's most luminous challenges. Some alternative ideas nudge the equations, adding fields or gentle modifications to explain cosmic acceleration or the strange pressure we call dark energy. These theories mimic Einstein's work in familiar regimes but deviate in extremes. To tell them apart requires measurements of rare sensitivity. New and future instruments, LISA listening from space, Euclid mapping cosmic structure, pulsar timing arrays feeling the low hum of the universe, are poised to search for subtle differences. Even the speed of gravity has faced its trial. When gravitational waves and light from the neutron star merger GW170817 arrived almost together after more than 100 million years of travel, the agreement showed that gravity moves at light speed to extraordinary precision. Entire families of modified gravity theories fell away in that single, elegant moment. The web of evidence is broad and tightly woven, from solar system shifts to pulsar clocks, from GPS corrections to black hole shadows, from laboratory gamma rays to space-time ripples. The testimonies converge. It is impressive to predict one thing correctly. It is something else to predict, with calm regularity, hundreds of outcomes across nearly every corner of physics and astronomy. And the very strength of such a theory invites scrutiny. The more a framework succeeds, the more we must explore its boundaries. Tests of the equivalence principle continue with ever finer care. Searches for drifting constants and quantum imprints in gravity go on. The aim is not to break the theory, but to find where it invites a successor. What endures about Einstein's work is not only that it passes so many trials, but that it dared to propose them. It gave us a map that explained what we had and pointed to what we had not yet imagined. It guided the building of satellites and observatories long before they could be realized. When the instruments finally opened their eyes and ears, the universe behaved as the equations had whispered. There is a quiet grace in that consistency. Chalk on a blackboard a century ago now, describing galaxies turning, satellites keeping time, starlight bending, and space-time itself trembling under distant dances. A human mind once traced the geometry of reality and found the world waiting there. And perhaps that is the deepest test of all. Not merely that the theory is true, but that it makes reality clearer. In the soft curves of space-time and the steady rhythm of falling things, we glimpse more than accuracy. We glimpse harmony, a tender concord between thought and the world it seeks to know. Two great ideas hold up the modern world of physics like twin pillars rising into the dark sky: general relativity and quantum mechanics. Each stands as a masterpiece of thought, elegant, predictive, and confirmed by experiment to breathtaking precision. Together, they describe nearly everything we can measure or imagine. The graceful arcs of planets, the shimmer of atoms, the rhythm of light itself. And yet, like two musicians playing in perfect time but in different keys, they do not harmonize. General relativity is the poetry of the vast. It speaks in the smooth geometry of space-time, the soft curvature that guides planets, bends starlight, and holds galaxies in their invisible embrace. Quantum mechanics, by contrast, rules the small. It hums in the flicker of electrons and photons, in the restless probabilities that define every atom. One describes the continuous flow of space and time. The other insists that nature comes in quanta, in indivisible pieces. In the gentle middle ground of daily life, this discord goes unnoticed. Our world is broad enough for both theories to work side by side without conflict. A GPS satellite is perhaps the quietest example of this truce. It keeps time through quantum mechanics, its atomic clock ticking by the rules of uncertainty, while its orbit requires Einstein's corrections for gravitational time dilation. One system, two languages, coexisting. But there are places in the universe where these languages collide, where immense gravity folds space tighter than light, and where distances shrink to the smallest conceivable scales, at the heart of a black hole. In the first trembling instant of the Big Bang, here, general relativity and quantum mechanics both claim authority, and their equations begin to disagree. Einstein's theory treats space-time as a smooth continuum, endlessly divisible. It is a fabric that bends gently or violently in response to mass and energy, following clear, deterministic laws. Given enough data, general relativity can, in principle, describe the future shape of space-time with certainty. Quantum mechanics rejects that certainty. It tells us the universe is stitched from uncertainty itself. Particles exist as clouds of probability, their paths unknowable, their energies discrete. The world it reveals is not a stage, but a restless sea of fluctuation. The two visions, one continuous, one granular, refuse to merge easily. To quantize space-time, to make geometry itself uncertain, has proven one of the hardest tasks physics has ever faced. Early attempts began with quantum field theory in curved space-time, a halfway house between the two domains. In this approach, matter and radiation obey quantum rules, but the space-time they move through remains classical, smooth, and silent. It works well in some corners, enough to predict Hawking radiation, the faint thermal glow that should leak from black holes when quantum effects stir the vacuum near their horizons. But it is not a true unification. The stage is still fixed. Only the actors dance. A deeper theory would let space-time itself become part of the quantum play. It would treat space and time not as infinite continua, but as discrete quanta, tiny grains, loops, or vibrations, each a fundamental unit of geometry. Among the most ambitious efforts to reach that goal are string theory and loop quantum gravity. String theory begins with a simple, daring idea that everything, the smallest particle, the greatest force, is made not of points, but of one-dimensional strings vibrating at different frequencies. Each vibration gives rise to a different particle, a note in the symphony of matter. The graviton, a hypothetical quantum of gravity, arises naturally within this music. In string theory, the universe holds more dimensions than the four we perceive. Some are curled so tightly that we cannot see them, folded into the fabric of existence itself. Within these hidden dimensions, the apparent clash between quantum mechanics and general relativity may dissolve into unity, a higher dimensional stage where both are parts of the same melody. Loop quantum gravity takes a different path. Instead of adding dimensions, it looks inward into space-time's own weave. It proposes that space is composed of finite loops interlocked in a network called a spin network, and that their evolution over time forms a spin foam, a shimmering lattice where geometry itself fluctuates. In this picture, space-time is not smooth at all but granular, like a fabric seen under a microscope. At the smallest scale, the Planck length, about 10 to the power of -35 meters, distance itself becomes discrete. Just as water appears continuous until we look close enough to see its molecules, space-time too may only seem smooth because our instruments cannot yet see its quantum grains. Both string theory and loop quantum gravity aim to describe a quantum geometry that becomes Einstein's space-time at large scales and quantum mechanics at small ones. Yet neither has been confirmed. The obstacle is not doubt, but distance. The effects of quantum gravity hide at energies unimaginably high, where no accelerator can yet reach. Still, scientists dream of indirect clues. Subtle fingerprints might lie imprinted in the cosmic microwave background, or in the patterns of gamma-ray bursts, or perhaps in delicate distortions carried by gravitational waves. Some hope that even the smallest violations of cosmic symmetries, tiny tremors in the constancy of light's speed or direction, could hint at the underlying quantum structure of space-time. Amid these speculations, one puzzle burns brightest: the black hole information paradox. In quantum mechanics, information cannot be destroyed. A particle's state may change, but its essence, the information that defines it, must endure. Yet if a black hole evaporates through Hawking radiation, and that radiation is purely thermal, then the information about everything that fell in seems lost forever. This defies quantum law. The paradox sits like a knot at the meeting point of the two great theories. Some suggest that information is not lost, but somehow encoded in the Hawking radiation, too subtly for us to yet decode. Others turn to the idea that information is stored on the black hole's surface, not within it, a revelation that led to the holographic principle. The holographic principle is one of the most startling insights in modern physics. It proposes that all the information inside a region of space can be represented on its boundary, like a cosmic hologram. The entire universe might work this way. What we perceive as three-dimensional reality could be a projection of quantum information written on a distant surface. This idea traces its roots to the work of Jacob Bekenstein and Stephen Hawking, who found that a black hole's entropy, its measure of information, is proportional not to its volume, but to its surface area. Later, through string theory and the AD-SCFT correspondence, physicists discovered mathematical bridges where a higher dimensional gravitational world is equivalent to a lower dimensional quantum one. The geometry of space, it seems, may arise from patterns of quantum entanglement, a network of relationships rather than points and coordinates. If so, then gravity, space, and even time are not fundamental. They are emergent, like sound emerging from vibrating strings or temperature emerging from countless moving particles. General relativity would then be a magnificent approximation, the visible calm of a deeper quantum storm. This view leads to an even more radical thought. Perhaps time itself is not elemental. In quantum mechanics, time is an external parameter, a backdrop against which events unfold. But if space-time is a quantum system, time might arise from correlations between other quantities, from the entanglement of states, from the statistical rhythm of the universe itself. Time may not be a river flowing forward, but a reflection of how things relate. These notions unsettle our oldest instincts. They stretch the imagination toward something almost spiritual in scope, a cosmos, where reality itself is woven from information and probability, where geometry is a shadow of connection. And yet, for all their poetry, these theories remain unproven. No experiment has yet revealed a graviton. No detector has glimpsed the discrete texture of space. Physicists continue to probe with mathematics, with analog experiments in laboratories simulating black holes and expanding universes, with ever finer observations of cosmic phenomena. The challenge is immense. But so was the leap from Newton to Einstein, from certainty to relativity. The tension between the great theories is not failure, it is promise. It tells us the story is not over. Both relativity and quantum mechanics work perfectly in their own kingdoms, yet nature contains both kingdoms at once, somewhere, hidden in the smallest vibrations of the largest curves. They must join. Finding that joining is more than a technical task. It is a search for coherence, for meaning. Because the question is not only how the universe behaves, but what it is. Is space-time a substance or a relationship? Is existence continuous or made of finite notes? Is time a measure or a melody? For now, we stand between two truths that do not yet touch. Black holes twist space-time into silence, while quantum particles dance in uncertainty. The universe expands, and electrons jitter, each obeying their own deep logic. Between them lies the next great idea, still waiting something beyond curvature and collapse, beyond wave and probability. Perhaps one day, we will look back on both relativity and quantum theory as stepping stones, brilliant but incomplete, toward a greater symmetry, a final simplicity. A theory that explains not only black holes and the birth of the cosmos, but why there is a cosmos to begin with. Until that day, we listen to the curve of gravity, to the whisper of particles, to the faint echo along the boundary between what we know and what we dream. And if you are still awake beneath this quiet sky, curiosity glowing like a small star behind your eyes, know that the journey continues outward, inward, endlessly. But if sleep has already gathered you, let it carry you softly, as space-time carries the galaxies through the calm between thoughts. Rest easy in that vast unfolding. The universe is still here, quietly breathing, waiting for you to wake and wonder again.